Okay, so the next speaker is Mustapha Maamache, and he's going to talk about time-independent quasi-Hermiticity. Hermiticity.
Okay, thank you. My talk is to revisit the quasi-Hermiticity, the time-dependent quasi-Hermiticity. And for this, I recall time-dependent, independent Hamiltonian, non-Hermitian Hamiltonian. For this, it was described by a stationary Hamiltonian where the non-Hermitian Hamiltonian is linked to Hermitian complex conjugate by this formula. And this formula where eta is the bounded inverse, or we call this the metric. And IH is an Hermitian Hamiltonian with respect a positive definite inner product defined by this quantity. And the eigenvalue of this Hamiltonian the spectrum is real. Is real, we can, for this reason, we can connect H to H dagger by this formula. And it was also established by Mustapha that the non-Hermitian Hamiltonian can be transformed to an equivalent Hermitian one by this formula, where rho is the Dyson map. This is the vocabulary of Andrea Fring. I don't know this. This is, we call this Dyson map. And when we go to time-dependent system, there is a problem. This is difficult to solve a time-dependent system in the case of Hermitian situation. There exists a method, one of sophisticated method in Hermitian cases is the Lewis-Rosenfeld theory. Lewis-Rosenfeld theory, what is Lewis? We have an invariant, an Hermitian invariant. We verify the von Neumann equation. And the state, this invariant have an eigenvalue of this invariant are constant. And the solution of Schrödinger equation ruled by the Hermitian Hamiltonian can be written as an eigenstate of the invariant multiplied by a phase factor. This is the case that I work in this for a long time. And in the case where the time, the Hamiltonian becomes time-dependent, with a time-dependent metric, there is a lot of point of view. And before starting studying this case, I recall that Maurice Faria and Andrea Fring have studied the time-dependent Hamiltonian with a time-independent metric. This is not the aim of this talk. And here we have this point of view. The first one is one is introduced by Miloš Noil. This is when we have to solve the Schrödinger equation, you map your solution by time-dependent metric And the state phi, the state phi is governed by this Hamiltonian, this generator, which is not observable. And Milosz states that is the quasi-Hermiticity for H. The second point of view is due to Mustapha Maamache when he said that we cannot have an unitary evolution and the observability of the Hamiltonian. If we state that we can have an observability of the Hamiltonian and the unitarity of the evolution, this coincides with H about this relation. In other words, the metric operator is time independent. There is another point of view of Andreas Fring and Musa when he mapped the map phi and the psi via the time-dependent metric. He obtained this relation, and this relation, he considered that this relation plays the standard quasi-Hermiticity relation for stationary evolution. And recently, Noil, in his recent work, has shed more light on the debate questions. My question now, how we solve Schrödinger equation, the time-dependent Schrödinger equation, non-Hermitian Schrödinger equation. It's very important. Without recourse to quasi-Hermiticity for Hamiltonian. There is, 2 days ago, Andrea Fring have speak about operator, a quasi-Hermitian operator. We use what we call the Lewis-Rosenfeld theory. Lewis-Rosenfeld theory in the pseudo-Hermitian cases is similar to the Hermitian one. This is exactly, we can, it's a similar. And the eigenvalue for this invariant are time independent. The pseudo product, scalar product, is given by this formula. This is exactly the inner product, the eta inner product. And the solution of Schrödinger equation, where the Hamiltonian is not Hermitian, can be obtained in the basis of the eigstate of the invariant with a multiplied phases. These phases can be determined from this one. And this is important because this phase is real. We have an Hamiltonian, a non-Hermitian Hamiltonian, and we have their evolution, the evolution state evolved with real phases. This is an important result. And this is the theory. We go to apply this theory to a systems. This system is the SU11 and SU2 Lie algebra, time-dependent non-Hermitian system. This, the Hamiltonian is described by a combination, a linear combination of the generator of Lie algebra, which obeys this relation, this commutation relation. And D here specify the nature of the algebra. When D equal -2, this corresponds to SU1 algebra, and when D corresponds to 2, this corresponds to SU2 algebra. We choose the invariant like the Hamiltonian because the algebra is closed. And we put this in this equation, in von Neumann equation, and we obtain our method is to get the pseudo-invariant operators. In other words, is to solve the quasi-Hermiticity relation. We use this operator, this is the Dyson map, with these parameters, and we obtain the invariant, the Hermitian. No, it isn't Hermitian. We impose that this invariant is Hermitian. For this, we impose the condition that this coefficient is real, and this, with this coefficient, are complex conjugate. This condition lead to these equations. And by imposing the quasi-Hermiticity, we obtain the pseudo-invariant operators. Now the condition, the invariance condition give this equation, which are difficult to solve this equation because in most cases this is nonlinear equations. And for simplicity, we choose that the parameter of the invariant are real. And in this case, my pseudo-invariant operator can be simplified and has this form, where we impose, because this is an invariant, K0, the eigenvalue of K0 are time independent, we impose that this coefficient is constant and equal to 1. And we obtain this. Finally, we obtain the solution of this equation of the SU1 and SU2 equation. The solution is given by this state, and just 1 minute, and we can apply this to a few examples. For example, the Swanson Hamiltonian, Non-Hermitian Swanson Hamiltonian, and for the spin in the magnetic field, and finally, because I haven't the time. Finally, we can also choose the parameter of the Hamiltonian real, and in this case, we obtain an interesting result that the quasi-Hermiticity, the standard quasi-Hermiticity for the Hamiltonian is verified. And the metric in this case is time independent. Thank you. Because in the program I have 20 minutes. Here we
40 other people with 40
2 minutes for
30.
discussion. 2 minutes in the it's not.
So, any questions, comments? Yes, please.
Just a curiosity, can I see something more about the Swanson model? How you introduce the time evolution in the Hamiltonian of the Swanson model?
This?
So it is in the parameters.
Yes. This is, we can obtain the solution. This solution is given by this Hamiltonian. And we can obtain the evolution operator, because here this state is time independent, is any state of K0. And we can obtain also this. This is this result has been obtained in with an invariant, with an Hermitian Hamiltonian. This is the same results. We can obtain the evolution operator. This is,
yeah.
When you say you can obtain them in terms of these functions psi and zeta, and you do not have explicit formulas for those.
okay.
They satisfy some other differential equations that you cannot solve exactly.
Exactly, yes.
This is like chance.
This, but I ask this from this equation. I said that this equation is very hard to solve. We haven't. We haven't a solution for this. This is, your question is interesting. We can study the adiabatic evolution in this case.
The Swanson model has actually been solved before by directly solving the Dyson, time-dependent Dyson equation. And as I argued, this scheme is entirely equivalent. So my question is, did you compare if your solution agrees with the previous solution?
For Swanson, for your paper?
Yes.
Yeah, for your paper. Yes. In your paper,
yes,
we solve the quasi-Hermiticity relation.
yes.
And you have the metric. You solve the metric. And after this, we have the Hamiltonian, the Hermitian Hamiltonian. And you go over to Hermitian invariant. Here, we go directly to...
I understand. We did this. I presented this. You can do it either way, but the result...
I haven't compared this. I haven't, because this is calculation is very hard. I haven't compared. Probably it's the same. I don't know. I don't know if it is the same. I haven't a response for this.
One more short question. No? Okay, then let's thank the both speakers again.
Thank you.